Now we're going to talk about the difference between ideal gases and real gases. So all along in this chapter, we have been assuming that the gases in all the questions, all the examples that we have looked at, were ideal gases. And basically, ideal gases are gases which obey the ideal gas equation. The PV is equal to nRT equation. Now, the thing about ideal gases at the microscopic level is that there are a couple of assumptions about their behavior. One of them is that ideal gases, when you look at the particles, there are no forces of attraction that exist between the gas particles. All right? That's the first assumption. For real gases, however, that's not true. There are intermolecular forces of attraction between the gas particles. And the result of that is that the pressure exerted by an ideal gas will be less than what you'd expect, or the pressure exerted by a real gas, I should say, will be less than what you'd expect for an ideal gas. All right? So that's one important difference between the ideal gas and a real gas. The ideal gas particles have no forces of attraction between them, but a real gas will have attractive forces between the particles, and therefore the real gas will have a lower pressure compared to the ideal gas under the same conditions. The second important difference between real gases and ideal gases is that in the case of ideal gases, the assumption is that the size of the gas particles is effectively zero compared to the container that they're in. We know, of course, in the case of real gases is not true. We know that the size of the particles in the case of real gases is a significant fraction of the total volume of the container they're in, all right? So that's another important difference between real gases and ideal gases. So what you'll find is that it is possible for real gases to approximate to the behavior of ideal gases. However, the conditions which would make these 2 points here become very important when it comes to differentiating between real gases and ideal gases is if the temperature of the gas is low and the pressure of the gas is high. Under these conditions, the gas will behave more like a real gas and not like an ideal gas. So in other words, if you want the real gas to behave more like an ideal gas, you need to have conditions of high temperature and low pressure, and therefore under those conditions, the real gases will behave like ideal gases. All right? And just to illustrate one important aspect or difference between real gases and ideal gases, remember we said that the attractive forces between the molecules in the case of a real gas would be greater compared to an ideal gas where the attractive force would be zero. And remember we said that the pressure for a real gas as a result will be less than the pressure exerted for an ideal gas. So that's what this is actually showing you. To the left, we have the representation of a real gas, or I should say an ideal gas, where there's no force of attraction between this gas molecule and the other molecules. So therefore, this molecule will basically travel at speeds that are high and will be relatively unhindered as it hits the wall of the container with full force. Now, in the case of a real gas where there will be attractive forces between this molecule and the other surrounding molecules, there will be a drag on this molecule as it travels, and therefore it will not hit the wall of the container as hard as in the case of the ideal gas. So therefore, as a result, the molecule will hit the wall with less force, and therefore the pressure exerted by the real gas will be less compared to the pressure exerted by the ideal gas. So this basically illustrates one important difference between real gases and ideal gases in terms of the pressure exerted by the different gases or the different types of gases. Okay, now in terms of the quantitative relationships between terms such as pressure, volume, and temperature, and so on, in order to get such an equation to represent what happens in the case of real gases, we have to make certain modifications to the ideal gas equation. So we're already familiar with the ideal gas equation, which is PV is equal to nRT. And a guy by the name of van der Waals, he looked at the behavior of ideal gases and he did his theoretical work, and he came up with an equation which is a modification of the ideal gas equation. And his equation, which is known as the van der Waals equation, is shown right here. And as you can see, it's a bit more complex compared to the ideal gas equation, where instead of just P, we have this term added to P, and instead of V in this equation here, we have this term minus NB added to the V term, and that product will be equal to nRT, all right? So that's basically van der Waals equation. And you see that there's some terms here like A and B. These are constant, which are related to different aspects of the gas particles. As stated here, A is a term that is related to the intermolecular force strength, and B is a term related to the volume of the gas molecules in liters per mole. All right? And these terms A and B would have to be experimentally determined, as you can see in the next slide here. I'm sorry, not that slide, but this slide right here. You have different values of A and B for different gases. So helium has this value for A and that value for B. Argon has those values, and so on and so forth. All right? So that basically shows you the relationship as far as the van der Waals equation is concerned, which is applied to real gases. Now, the last thing I want to show you in this particular chapter is this particular slide, which I jumped over. This shows you graphically the difference between an ideal gas and real gases, but also it shows you how the temperature can affect the real gases so that it can actually behave more and more like an ideal gas as the temperature increases. So we all know that PV is equal to nRT, all right? Now, assuming that we're dealing with 1 mole of a gas, that means that, and let me go back to my pen function here. That means that if N is equal to 1 mole, hold on, wait a minute. If N is equal to 1 mole, then that would be equal to PV over RT. So PV over RT is going to be equal to 1. So basically, for an ideal gas, it doesn't matter what the pressure is, the arrangement of PV over RT is going to be equal to 1, which is shown here. All right? So that's what this dotted line here represents, the plot of an ideal gas when you plot PV over RT versus the pressure, right? Now, the other lines or the other curves that are shown shows you the plot when it comes to the same gas, or I should say not the same gas, but a real gas as the temperature changes. So the green line represents the plot when the temperature is 200 Kelvin, and then the red line here represents a plot when the temperature is 500 Kelvin, and then this blue or purple line here represents a plot when the temperature is 1000 Kelvin. And if you look at these curves and these plots closely, you'll see that as the temperature increases, the curve basically flattens out, all right? So the green curve is like this at 200 Kelvin, and when you compare it to the red curve, it is a flatter plot, more approaching a straight line plot for the ideal. And then by the time you get to the curve representing the plot at 1000 Kelvin, it's almost a straight line, but it's pointing up. So you can imagine as the temperature increases, the plot will become more and more like a flat arrangement, a flat line, which is what the ideal gas plot is. So basically what this is showing you is that as the temperature increases, which we said before, as the temperature increases for the real gas, it behaves more and more like an ideal gas, all right? Okay, so that's basically it for chapter 5. And then the next video now we'll be moving on to chapter 6, which deals with thermochemistry, all right? Okay, until next time.